Great. Good morning, and thanks again for coming up to SLAC. Last year I had the opportunity, being relatively new here, I came and sat in a couple of these sessions along with you because it was a great chance for me to learn more about some of the activities that were going on in campus and a way to kind of figure out what some of those pathways might be for some of our research. And that continues to be a big part of my role here at SLAC is identifying capabilities and people here at SLAC and people at Stanford that we can put together and make some of these good things happen to help solve the problems Tom alluded to. So let's see. Just manual. Okay, thanks. So the first part of my talk I'll blow through really quickly because I think Tom covered a lot of this. You know, as he said, last year was our 50th anniversary. Just to put SLAC in context for you, we are one of 10 DOE laboratories operated by the Office of Science. Our total budget is around $370, $400 million, and there are about 1,700 people who work here at SLAC, and about half of those with advanced degrees performing science. The other thing that you'll see as you take your tour today is that we have these user facilities that Tom talked about, the Stanford synchrotron and the linear coherent light source, and actually the FACET facility, which looks at advanced accelerator concepts that are user facilities. So people can come from all over the world, and they do, to take advantage of the kind of research that they can do at these unique facilities that we have here. Many of these people are collaborations with Stanford who will come up and do this as part of their thesis research. So it's been funny as I've gone around and talked to people in different agencies back in DC or other places, and I'll say, what do you know about SLAC? You know, 1 out of maybe 10 people will say, oh yeah, I did some work at SSRL on my thesis at some point, whether they were at Stanford or not. So that's what a lot of people know us from because of the exposure we get from that. Tom already covered this slide. You can tell we're very proud of the Nobel Prize legacy we have at SLAC, and we hope to be adding some more to that queue fairly soon. We did undergo this transformation, and as we really started with a rich history of very fundamental particle physics, we've really shifted gears in the last few years to become this photon science laboratory. So that means building and operating these world-leading facilities. And the LCLS, which I'll talk a little bit more, and we'll even show you a little movie about how it works, you have to understand how unique that is in the world. And it was really a remarkable concept, design, execution, and is now being used to just do some of the most amazing science in the world. So it's the success of getting that up and off the ground has been phenomenal, and it's part of the reason that DOE is invested in sort of expanding the capacity because it's so precious we can only take about 1 out of every 6 or 7 proposals that people send in to us requesting the beam time on that. And it's the science that we're doing at this facility, not only internally here with partners at Stanford, but with people around the world is really, really exciting. You know, we have a strong legacy as an accelerator laboratory, and now we're looking to take some of these technologies that, you know, are the very kind of same things that the Varian brothers developed the Klystron back in World War II for radar, and that's kind of a legacy here. You find it used in medical imaging. You find it used in semiconductor technology. You know, we're looking today to see, is it possible to do, you know, waterless fracking by putting microwave energy downhole to cause some of the same kinds of fractures that people are looking at. So we continue to look for new kinds of applications that people can extend with that. And then the Kavli Institute in particular, the building behind us, is really kind of a lead in cosmology, and Tom alluded to that, but I won't talk much more about that in today's talk. This kind of pictorially shows, again, that reinvention. So this was in 2007 when we were still running the linear accelerator to do particle physics experiments. So you see that in red, and the little circle in the middle was the X-ray synchrotron that we had and still have today. But in 2009, we basically converted the last third of that linear accelerator into the driving force that produced electrons that went through the undulator to make X-rays and created LCLS. So let me give you a little bit of an example about this and try and give you an analogy that helps put it in perspective. But I'll start first with a setup. How many of you remember this moment from about a year ago? Governor Romney, in the middle of a debate, reached over to Rick Perry and said, I'll bet you $10,000, right? So it turns out that governors have a long history of making bets, and we'll pull this back to a Stanford story. How many of you know this story? Anybody? 1 or 2, okay. So this is you know, kind of put yourself back in context in the 1870s or time frame. Nobody knew what a horse galloping looked like, right? Nobody could actually ever see that. It was too fast to resolve with the naked eye. And supposedly, Governor Stanford bet somebody $50,000 that the horse's hoofs came off the ground. So 1878, $50,000 was a lot more money than $10,000 was last year, right? I mean, that's kind of the gold Tom was talking about, I guess, right? But the way they solved this problem, you know, back in that day, and this was sort of the early days of photography, the way you controlled the shutter speed with a camera was by taking the lens cap on and off, right? Not a very fast solution. Even if you did it really fast, you're going to get maybe a half a second shutter speed, and you won't be able to do that. So what Maybridge did is he invented a mechanical shutter that would slide across that, and it was connected to a set of wires that ran across the track. And this was done not too far from where the football stadium exists today, where they did this experiment. They set up a series of trip wires, a set of cameras. The horse ran through there, hit the wires, took snapshots really quick, and you put them all together. This is actually 16 still photographs that are put together and show that definitively the horse's feet come off the ground when he's galloping. So the real insight here is, you know, this was a challenge. This was a problem that people were trying to solve. It's a little trivial compared to today's energy problems, but it took a new tool and a new idea to figure out how to do that, right? So LCLS is essentially the same kind of idea. If we think of, you know, on the order of milliseconds to microseconds is what a camera shutter speed does today. You can freeze motion and stop things, and you can look at, you know, things in nature like a hummingbird wing or how a protein folds. The synchrotron radiation light source, the SSRL, can get to fairly fast times. It'll get down close to a picosecond, right? So you can start to look at molecular group motion, vibration in molecules. It's comparable to how long it takes to write a bit in a computer. But when we get to the LCLS, we're talking about femtosecond timescales, right? And we're getting now down to, you can't see this on the bottom, but you know, the time it takes an electron to orbit a hydrogen atom is on the order of a femtosecond. So we're getting to the point where we can start to have a tool which is so exquisite that we can look at things on that time scale. And again, at an incredible spatial resolution as well, because we're using hard X-rays to do that. One of the ways that we're doing this, and one of the things that we can do, which is really neat, one of our sort of holy grails for LCLS, is being able to look at proteins that don't even crystallize, which is a requirement to be able to look at them with a conventional X-ray. And we had to develop a new technique for this as well. On the bottom, you see the free electron laser pulses coming in. They come in at about 120 hertz, and they're really, really short bursts of energy. In front of that will feed in droplets of particles or droplets of liquid that contain proteins that aren't even crystallized in many cases. And when they interact, it actually destroys the protein. But to give you an example again of the time scale, the electrons or the X-rays pass through the protein and give a diffraction pattern before it actually blows apart, right? The time scale on which the atoms move is slow enough that you can still get a diffraction pattern out of this, despite the fact you've even, you know, the molecule falls apart in the course of the experiment. So we call this diffraction before destruction, and it's turned out to be a really powerful technique. We've looked at things like photosystem 1. How does photosynthesis work? Nobody really has a good handle on that, and this can really be a key to understanding how do you split water, how do you convert CO2 into sugars or things that could be fuels. A lot of biological applications with things like the Mimi virus. We've got a strong program we're starting up now, which is looking at creating ultra-bright, ultra-intense energies using shockless collisions that we can do. We have one of the stations that you may see at the end is called Matter Under Extreme Conditions. We can create something which looks like interstellar kinds of capabilities, temperatures and pressures, and study that, again, with the details we have there. This actually could be very important looking at fusion applications, so there's a lot of energy connections back to that as well. The synchrotron is a great example, and one of the things that's nice about this is and I don't know if you'll get to this on the tour, but electrons run around the ring continuously, and so we have about 30 different beamlines off of that. We can run simultaneously a number of different experiments. Some of these stations, again, have a queue of people waiting to get their time on there and be able to go in and do their science, and I'll give you an example of some of the things that we're doing there as well. You know, one of the technologies that we've recently developed is what I jokingly call kind of a CAT scanner for batteries. You know, maybe you've had a CAT scan, you've gone in and you know, you get this exquisite image of what goes on inside your body if you're sick. Well, why would you want to do that for a battery? There's actually some really interesting applications. This is what the tool actually looks like that exists at the end of one of the end stations. But, you know, today's challenges, as Tom showed in his talk, is, you know, we need to get the energy density up. We need to get the power delivery up out of that. And if you're this is work from Professor Will Shui, and I'll give a little plug. If this intrigues you, he's actually giving one of the master classes tomorrow afternoon. But he's a new faculty here who's got a tremendously inventive set of tools and ideas to try and get to some of these problems. Most of these batteries are made of nanoparticles, right? And there's a variety of different chemistries. Here he's looked at iron phosphate for this. And one of the questions nobody's really understood is you've got this enormous collection of billions of nanoparticles in a battery electrode. When you start to charge that and discharge that, lithium goes in and comes out of those particles. How does that work? Do they all kind of go simultaneously and then they all kind of give up their lithium simultaneously, or is it sequential? And he's able to get some insight into that by looking at this. And by using the X-ray absorption spectroscopy, you can see what particles have lithium in them and what don't. And by looking at this, he's able to see that, if at any given time during a charge and discharge cycle, if you looked at and examined that, you'd find that there's some particles that are completely lithiated and there's some that haven't even started yet. So that tells you that they're not all kind of working in parallel, that it's kind of a sequential thing. And that has an important application for how fast you can accelerate when you step on the gas pedal in an electric car, for example. If you're only getting a few of these things that are discharging at any one time, it's far different from getting a little bit out of every one of those particles. So you can see that it's a really fundamental application and understanding of how these things work, but it has really important applications in a practical design for something like that. So again, I'd encourage you to maybe, if that's intriguing, to check out Will's class tomorrow afternoon. We're doing the same kind of thing with this X-ray microscopy looking at catalysts. So catalysts are important for a number of industrial processes, and people are looking to develop new catalysts for ways to do everything from CO2 conversion to fuels to methanol oxidation to you name it. There's a variety of different things here. And with this same X-ray capability, what it really gives us the power to do, in a lot of cases people had started out by saying, they make this sample in their lab, they run it for a while, they'll pull it out, and then they'll send it off to get analyzed. We're getting to the point now with the batteries, with the catalysts, that we can start to look at these things as they're operating the way they normally would. And so you've got this tremendously useful tool, but you're seeing things happen in real time. And so we can do that by taking a CAT scan of the batteries, or in this case, the catalyst particles. And so you can see that here's an iron oxide particle that undergoes an oxidation state change during Fischer-Tropsch synthesis. And we're able to come in and look and see what are the active parts of the catalyst particles. What are things that sort of die and decay? Does it happen uniformly again? So again, really important information, which is fundamental to understanding what's really going on in these applications. Another part of the catalyst development that we're doing is actually on the theoretical side. And computing has advanced to such a tremendous degree that in a lot of cases it's easier to do experiments in silicon rather than it is to do them in the laboratory. And here's an example of this. In the SunCat Center that Tom talked about, Jens Norskov and his team are looking at, in this case, is methanol dehydrogenation. And it's a multi-step process, but if you look at what you think some of the rate-limiting steps are and what the activation energies for some of those steps are, depending on the catalyst, and he's shown here single metal element catalysts and how that would work, you can get a lot of insight into what's the right combination of materials to try, or what are some of the things that we think might be the set of catalysts to prepare in the laboratory and evaluate, and really narrow down the range of possibilities for what you have to do. And oh, by the way, he's got an app for that, so you can check out with your iPhone what the best catalysts are for a variety of different reactions. So, 21st century science here. Coupling that kind of capability for the design of experiments and the theory with the synthesis capabilities we have and the characterization capabilities that we have really gives us the ability to close this circle, do rapid learning cycles, and really make progress on some of these really challenging issues. So it's a great opportunity to complement the theory kind of work we do in catalysis, or some of the things that Tom does in condensed matter physics and correlated materials with the kinds of experimental capabilities we have here. So it gives us a great ability to make that happen full circle. Lest I leave you with the idea that we really focus only on basic research. That's kind of the main thrust here, again, given the tools and given kind of the funding streams and the areas we work with. As I said, one of the real challenges is the opportunity to take that and go make impactful things happen. I don't think Nick is given one of these courses tomorrow, but another professor at Stanford in materials science started looking early on at diamondoids, which were these sort of, 1 or 2 unit cells of diamond material that people were getting out from oil, and working with Chevron, and said, what can I do with these things? Turns out they have some really interesting electron emission properties that can give you a very narrow distribution of electrons coming off a surface. So that's really important to some place like SLAC, where we start the LINAC with a photocathode, where we hit it with a laser and electrons come off. If we can get a narrower spread at the beginning, that makes the optics easier for the next mile or 2 miles of delivery we have to do. But it also has some really interesting applications for electron beam lithography, for data storage ideas. And actually he turned this into a proposal looking at how can we do improved efficiency in a solar power tower by getting some direct electrical energy and then using the waste heat to harvest through the normal thermal storage cycles. So we've had, I think this is one of the quintessential examples of a deep understanding in the fundamental science can then turn into some applications, and we're looking to leverage those kinds of things more and more and more. So I hope you have a great tour and a great experience up here. I guess I want to leave you with just a couple of things. SLAC has really just tremendous capabilities and tools, not only in the research facilities we have here, but they're unique enough that it really requires some expert to figure out how to use them. And we've got those experts here, and they're always looking to collaborate. We have a lot of students who come up here. So as you start to develop your program, think about opportunities that we can help and contribute to that. The combination really provides a unique research opportunity, and that ability to take something from a really deep fundamental understanding of how a system works and then translate that into the applications. And I gave you just one example, but there are lots of those in batteries and catalysis, in electrochemistry, and a variety of things. So, take advantage of that. The other thing, and one of the things I enjoyed last year as I spent a little more time with people is that, this isn't all just the science grad students. There's people in policy, there's people in law, there's people in business school. And so Stanford is really unique in that ability to be able to bring those disciplines together. You don't find that combination in many other places. So, when I first heard from Lynn Orr the concept of this, bringing people together and building this network beforehand, it sounded like a tremendous idea. And so I think you guys need to take advantage of that. I spent my first 10 years as a research scientist working in the lab, and then I ended up doing a AAAS fellowship down in DC, and that was kind of my introduction to science policy and science research funding. And it was a tremendous sort of career change for me, and it turned out to be something that's really interesting. If I'd had the opportunities of sort of the rest of that to complement the science skills I had when I went to school, I think it would have been something I wished I had to take advantage of. So I encourage you to work on that here as well. I'm happy to take a couple minutes of questions, but I've got to actually run to the airport, so maybe 5 minutes or so would be great. Thank you. Another question?
Along with that, do you guys collaborate with LBL?
Yeah, we actually do. And in fact, the battery research that I showed you from Will Schway, part of that work has been done up at LBL. We're actually about to enter a joint program with LBL and the California Clean Energy Foundation in something called CalCharge, which is really focused on taking research in batteries out of the lab and helping to apply that into manufacturing with a number of the startup companies that are in the Bay Area here as well too. Getting them more familiar with the capabilities that both the labs have, and they're very complementary to be able to do that. Yes?
Like you said, you have a funding budget of about $370 million in your DOE lab. How much of that is actually coming from the DOE and how much from other sources?
95% of that comes from DOE. We get a little bit from NIH for some protein work. We get a little bit from Department of Defense for some of the materials and advanced accelerator concept things. And we get a little bit of industrial funding that's coming. But my challenge is to help make that, move that needle from 97% down to about 90% or so and bring in some of these additional opportunities. And so I think we've got a lot of capability to do that.
I wanted to ask how many Stanford research groups are based on the campus?
I don't know, Tom, maybe you've got a better handle on that. Many of them fall under the SIMES and photon science area.
Well, I think all of the staff scientists are based here, and in terms of particularly the ones that like Stefan, who's going to be talking next at SSRL and LCLS. I don't know the exact number of staff scientists, but it's on the order of 100 for sure. For SLAC Stanford faculty, there are probably on the order of about 50 or 60 PIs that are operating groups that are based up here to various degrees. And that's one of the wonderful things about the fact that there's only the golf course between Stanford and SLAC, is there is a constant flow back and forth. For example, many of us have offices down on Stanford and up at SLAC, so we're able to make transitions in some cases every single day. But yeah, that's there is research that the research that's happening here is here for a reason, that is coupling to the activities that are more SLAC-based.
One of the visions that we actually have is that it shouldn't take a 3-kilometer long LINAC or a 15-mile radius, storage ring to be able to do these kinds of experiments. Continue to do things like medical treatments. We're actually working on things that are, today when you try and do cancer treatment for somebody, you have to go through an awful lot of work to try and immobilize the patient and get things to happen. It's a huge facility today for even, sort of high energy photons, and even bigger if you tried to do something like proton therapy. If we can make a really compact accelerator, that can open the doors to making that kind of technology, proliferating everywhere, right? We are just scratching the surface of the kinds of things we can do with materials understanding and biology understanding with things like that. So the ability to make something like what SLAC has today pop up at universities all around the world will just open the door to all sorts of discoveries and capabilities. So we're trying to enable that.